7.3 lesson. So electrolysis is basically driving our voltaic cell backward. We're going to cause a chemical reaction by putting in electricity. It's kind of like recharging the battery. In fact, many cases, it literally is recharging the battery. We're going to drive chemical processes against the spontaneous direction by putting in electricity and forcing them against the will of nature. First off, though, a Faraday is the charge of a mole of electrons, which I think I've said before. Basically, here is Faraday's constant. It converts between a Coulomb and a mole of electrons. If this is a Faraday, then this is the ratio between a Faraday and a Coulomb. So also an amp. So that's an ampere. There was a Mr. Ampere, and an amp is a Coulomb of electrons going by every second. Of course, you can have more than one. You can have half. You can have 0.869, whatever. But 1 amp is 1 Coulomb of electrons going by per second. Also, for reasons I never figured out, current is marked with a capital I. I think that stands for inductance. And notice it's charge per times the concept. The concept, again, is charge per time, but the units is a Coulomb because that's a certain number of electrons per second. That's the time. This is the symbol for a battery. And so what we've got here are two charged plates. And so electricity is going to pass between the plates through the water. Now, if you drive the electricity hard enough with enough voltage, you can overcome the covalent bonding in water and you can separate it out. And this is electrolysis of water. So in case you're really interested, we can talk about the details of the reaction of the water getting electrolyzed. This is not super important to understand. You can skip it for the rest of the course. But we're supplying electrons from the battery. Here they come. They're coming off this electrode here. So the part of the water that might accept electrons is the part that's positive. Now, H has a positive 1 oxidation number. So they might accept 1 electron each. And what it makes is the elemental state. Now, I realize this is 4424, and that's all even numbers. Let's kind of ignore that for a moment. It'll become apparent. You might look like a mistake. And I'm going to teach right at the moment about different numbers. So what you get is an H2, and that's a charge 0. So each of the H's coming off here has gone from +1 to 0. Now, what is not obvious is that you only get 1 H off each water. So it takes 2 waters to form one of those. And I know there's a 2, let's ignore that. So then we get 2 OH minuses that are left from breaking up 2 waters. And that took 2 electrons. So really what we have is 2, 2, 1, 2. However, the circuit must complete. The battery or the whatever's supplying this electricity is not going to keep running if it doesn't get some electrons back. So something must be oxidizing to complete the circuit, giving electrons back to the positive part here. So it's the oxygens that would do the oxidizing because they have an oxidation number of -2, and they could go to 0 in the elemental state here. So of course you only get 1 oxygen per water broken up, and you need 2 of them, so you need 2 waters there. That forms 1 O2, and 2 electrons came out each, so that's 4 electrons that came out total, and you get 4 H pluses out of 2 waters. Now this balances in its most simple form with 4 electrons, so that's why we have to go back to this half reaction and multiply everything by 2 so that that's 4 electrons. Because the electrons going into the reaction must be the ones coming out and so forth. So now the electrons cancel out, and when you cram these 2 half reactions together, we get the overall reaction here. And now we don't have all even numbers because that's odd. And when we made the overall reaction, you can notice here that the H pluses will combine with the OH minuses and make water back. So we started with some waters, we ended with some waters, and we end up with 4 waters on the right side, which cancels out 4 waters on the left side, which is an answer for why we only have 2 waters on the left. As I said before, the H's are receiving electrons because they're going from +1 to 0. The oxygens are giving electrons because they're going from -2 to 0. So the one that's generating the most gas is the one where the H's are being produced. And we said the H's are receiving electrons. That's reduction. Reduction is the cathode. The electrode on the left is the anode, and the electrode on the right producing H2 is the cathode. And of course, we know that they're going this way. If this is the symbol for a battery again, that's the minus. The electrons are going through this way, and then they complete the circuit through the wire to the battery here. So what's the overall voltage potential for this reaction system? Well, we go to our standard table of reduction potentials, and the reduction potential for this is positive 1.23 volts. Now, somebody says, but you said it's a negative, right? This is getting oxidized. Remember, the oxygens are going from -2 to 0, so the oxygens are losing electrons. Look, there they go away. This is an oxidation reaction, so the sign flips from the table. This is a reduction reaction, and we look it up, and it's minus 0.83 volts. So we do have an oxidation reaction and a reduction reaction. And then somebody says, no, 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 you must have made a mistake because you said that the total must be positive. That is for reactions that nature favors. Nature doesn't favor water just falling apart. Nature likes water being water. It's a very low energy, stable molecule. This only happened because we shoved electrons at it pretty hard. This is not a favored reaction, and the total voltage is not a positive. It's very much a negative. And you have to really do some work to tear water up like this. You have to push electrons at it with greater than 2.06 volts. The process is non-spontaneous and requires an external power source. You bet it does. Greater than 2.06 volts to drive it. So one choice for an electrolyte that's a plus-minus pair that you dissolve into the water to encourage the electrical flow is sodium sulfate. And we know that sodium is a super soluble, and these are all going to dissolve very well. Now, there is, though, the thought, if you're shoving electrons at things, why wouldn't the sodium take one? Well, sodium is an alkali metal, and they love being positive one, and they hate being charged 0. So you can imagine that they have a resistance to having the electrons stuck back on it. And they do, and it's a fairly strong one. If you want to run this reaction and stick the electron back on sodium to make it charge 0, you have to supply electrons with a voltage of greater than 2.71 volts. Well, that means that this reaction is easier to drive than this one, and this one will happen before this one will. The electrons will stick in here and cause this reaction before they do this one. They do allow themselves to ask about amps. And remember, an amp is a coulomb per second. So here's an amp flipped upside down. Apparently, we need to run it this way to cancel out everything. Well, what is the question? How long does it take to generate 1 liter of H2 gas? Okay, so what we need out of this is seconds, which kind of proves the point that this is going to have to be upside down, so to speak. I need seconds to come out as the unit. So what do we know? 1 liter of H2. Now, it says 1 liter of H2 gas. What they mean is at STP, of course. They should have said that. And at standard temperature and pressure, there are 22.4 liters per mole. This lets me cancel out the liters. How many electrons come out of that? If we look at this closely, we can see that when we generate 2 H2s, we need 4 electrons. So that means the ratio is 2 to 1. I mean, we could put 4 to 2, but it's also 2 to 1. You need 2 electrons for every 1 H2 you generate. So for every mole of H2 gas we create, we're going to need 2 moles of electrons. Now we have moles of electrons. But I need it in seconds. Current isn't measured in moles of electrons, it's measured in coulombs. So I'm going to convert out of my moles of electrons. I'm going to grab Faraday's constant, flip it correctly so that the moles of electrons cancel out and give me coulombs, which is a different group of electrons. Except I need one more conversion because I don't actually want coulombs. I want seconds. Well, I know that in this case, the ratio of coulombs to seconds is 10 to 1. because it says I'm running 10 amps, and an amp is a coulomb per second. So I am running 10 coulombs per second. Multiply by the top, divide by the bottom, double check your canceling, and you get 861 seconds. On the back, we talk about generating that solid sodium that we said was not going to be possible when we had water present. Well, we're not going to have water present. We're going to melt table salt, and boy, that takes some work. It apparently melts at 801 Celsius, so that's not easy, but apparently we've done it. So this is a pool of molten table salt. Ouch. And we have graphite sticks here that are electrified by our battery. So we're trying to produce solid sodium from sodium plus. That means it must be taking on electrons because it's going to get more negative and turn to charge 0. So this is the receiving of electrons. This is the reduction. This is the cathode. Therefore, the opposite post of the battery must be attached here. This is going to be charged positive. It's going to attract the negative Cl minuses who are going to give up their electron and turn into Cl charge zeros, elemental state charge 0. Now, as I said, they're going to give up, so they are losing 2 electrons, or 1 for each ion, turning into 1 each atom. We look on our standard table of reduction potentials, and we can see that this one is run backward on the table and has a positive 1.36 volts. However, remember, we're not going to run reduction with this. We're going to run oxidation. So from the table, we'll flip this around so it's like this, and then the sign flips to be a negative voltage potential. This is reduction, and on the table it'll be written like this, and it's negative 2.71 volts. Well, we have 2 negatives, and again, we're not saying that nature likes this reaction. We're not saying that nature performs this reaction on its own in any sense. This is a negative, and the overall voltage is a big, big negative, at least by these standards. It takes a lot of electricity. Nature hates this reaction. You have to really force it and really push in some electricity to get it to happen. So we're going to have to double this line, though, to get the electrons to cancel out, and then combine everything. And remember, that's a liquid because it was melted. It's not a solid. It's not aqueous. And we generate the elemental forms in the end. So this might seem like it's impossible at first. How would I know what mass of sodium is produced? Well, just assemble all the conversion factors you can think of and start flipping stuff until it starts to look like they're canceling out and going somewhere you want. I mean, if you're really stuck, what do I want? Grams of sodium. Well, you know what? When we talk about grams of things like sodium, elements, we don't work in stuff like coulombs, do we? No, we work in moles. So what I know is coulombs per second. Also, I know seconds because 1 hour is 3,600 seconds. So what I can do is use my amp figure to cancel out the seconds to give me coulombs. Again, though, when I want grams, I'm going to need moles. So I'm going to get moles of electrons by using Faraday's constant, kind of upside down, so to speak, cancel out the coulombs, give me moles of electrons. Now, when I produce 1 solid sodium, I need 1 electron, actually better illustrated here. So it's 1 mole of each, but this cancels out the moles of electrons, gives me moles of sodium, and at that point, it's pretty trivial to convert to grams of sodium produced.